So let's first talk about section 2.6, which is linear approximations and differentials. So let's first take a look at the picture on the right hand side. So suppose that we have the curve y equal to fx. This is the one that I just highlight in light blue. So I have the curve y equal to fx, and I am focusing on the point A and FA here. So we know that the tangent line at the point A, comma FA is the line that I just draw in green here. This is called the tangent line, right? At x equal to A. And the equation of the tangent line is going to be y minus A. Oh, sorry, y minus, let's start from y minus y naught equal to the derivative, right? Slope m times x minus x naught. So here, if you compute the derivatives, so you're gonna get f prime A. And if you plug in the value of x, which is A, here in x naught, and then you can plug in the value of y, which is fa here. So it's gonna be y minus fa. And if you simplify a little bit, so you're gonna get this equation. So this is the equation of the tangent line at the point A, comma fa, right? Well, the idea is, so if you take a look at the equation of this tangent line, so you're gonna see that we can find the value of the function fx at the point near x equal to a by using the tangent line as the approximation. By this I mean, if you take a look at the picture, you can see that, hey, at the point x equal to a, this is the point that the line, the tangent line touch the curve, right? But at the point that, let's say, very close to x equal to a at this point, so you can see that the value of y on the tangent line and on the curve, right, they are very close to each other. So that means we can approximate our function fx by using the function that we have from the tangent line. This is going to be a good approximation when x is near a, right? You can see that if f is near, if the value of x is near the point A, so the approximation is going to be better. But if you point at the value of x that is far from a point A, so that means the approximation is not going to be good, because the real value is going to be this red point, but your approximation is going to be this green point. So you're going to have a gap here. This is your error, right? So the idea for this section is, when x is near a, we're going to approximate our function f by using the linear approximation. This is my linear approximation. Just using f at the point A plus f prime at A times x minus A. So let's look at that linear approximation by doing examples. So this is our theory. So maybe you are a little bit confused now because it is all symbols now. So we are going to look at example and hope you feel better after you see the first example here. So let's take a look at example 53. Let's suppose that I have the curve fx equal to square root x plus 3, right here. And then I want to find a linear approximation of the function f at the point x equal to 1. So linearization means linear approximation. So we want to find a linear approximation of a function f at the point x equal to 1. So the equation of the linear approximation is if you want to find the linear approximation, well, we're gonna label it as our function L. So our function gonna be L equal to fa plus f prime a times x minus a. Well, this equation, I got it from the one that I boxed in gray now, right? So, but I just name it Lx. So this is my linearization or linear approximation of f at a. So it's going to be fa plus f prime a times x minus a. So what you can do here, you're going to plug in the value of a. So x equal to 1 here means a equal to 1, right? Because we are looking for the approximation at a. So a equal to 1. So this is going to be f1. And this is going to be f prime 1. And a equal to 1. So this is going to be x minus 1. And now you can find the value of f1. So you plug in x equal to 1. So you get square root 1 plus 3. And then f prime 1. So that means here you need to compute f prime. So you have fx equal to square root x plus 3. Right? That means f, well, let's simplify it to x plus 3 to the 1/2. And then when you differentiate, so you're going to get 1/2 times x plus 3 to the negative 1/2. And then by the chain rule, you need to differentiate inner function. But here, differentiate inner function, you get 1. Because you differentiate x plus 3. So you get 1. With less, differentiate x plus 3 with respect to x. So you get 1. Well, that means your f prime x going to be 1 over 2 times square root x plus 3. And that means f prime 1 is going to be 1 over 4. Right? Well, that means I have 1 over 4 here. And then I have x minus 1 here. Well, if I simplify this thing, I am going to get 2 plus 1/4 times x minus 1. And then you simplify this, you're going to get 7 over 4 plus x over 4, right? Because 2 and negative 1/4. So you get 7 over 4 and then plus x over 4. All right, so this is my linear approximation or linearization. So actually it is the equation of the tangent line here. And we can use this function to approximate the function f. So you can see from the table that, look at the table here. What I am going to show you is when x equal to 1, you see the one that I highlight? When x equal to 1, you can see that the actual value of f is going to be 2. Because if you plug in x equal to 1, so you get square root of 4, which is 2. And then that's the actual value. And then if you use Lx to approximate, that means you plug in the number x equal to 1 into the function. So you're going to get 7 over 4 plus 1 over 4, which is 8 over 4, which is 2. So that means the approximation is exact at the point x equal to a. But when you look at the point x equal to 0.98, so I'm going to switch the color. So 0.98 here. So the actual value is going to be 1.994. By this, I mean, if you use a calculator to compute 3.98 take square root, so you're going to get this number. But if you do not want to use the calculator, you can just plug in number 0.98 into the function L, and you're going to get 7 over 4 plus 0.98 over 4. And what you get is going to be 1.995. And we're going to use 1.995 as our approximation of square root 3.98. Does it make sense? So this way we can avoid the hard way to compute square root, right? So we can just, okay, I have square root function. So I am going to approximate it by using a linear function, which is easier to compute. You can see that, let's suppose I look at the point x equal to 1.05. So the actual value is going to be 2.01246. This is the actual value for square root 4.405. If you use the calculator, this is the actual value. But well, we can approximate that thing by using 7 over 4 plus 1.05 over 4. This is my approximation. So the idea is, I would say it again. So the idea is we're trying to use linear function as our alternatives to approximate the harder function. Sounds good? So this is how we use the linear approximation. All right. So let's dig into this thing more in more theory. So we are going to look at, we are going to define the term. The new term that we are going to define is differential. So differential, well, this is defined to be dy equal to f prime x dx. So this is a notation for differential. So we are going to use a notation dy to be our differentials. So differential is defined to be f prime x times dx. So if I want you to compute differential of the function x squared, so what you get is you have to differentiate to x squared with respect to x. So you're going to get 2x and then multiply the x. Done. This is called differential. Let's say I want to compute differential of cosine 3x. Well, that means I need to differentiate cosine 3x. So I differentiate cosine, I get negative sine, right? Negative sine 3x. And then because of the chain rule, I need to differentiate inner function, so I have 3. And then I attach the x. Done. And then let's say I have the like x times sine x, for example. Well, this thing I need to differentiate by using the product rule, right? So it's gonna be x, and then I differentiate sine, I get cosine, and then I keep sine x, and then I differentiate x, I get 1, and then this dx. So by this I mean if you have the fx, whatever fx is, so you just differentiate them and attach the x at the end. So differentiate fx, so you're going to get f prime x dx. Well, we're going to use this notation. We will use this notation later. So we're going to use this notation to define our differential, to define our linear approximation, and to define, to help us to integrate later in the next chapter as well. So this is how we define differentials. So let's first talk about how differential is related to linear approximation. So after I define the notation dy, so the next step is, well, let's look at the difference between the notation dy and the notation delta y. So if you look at the picture here, I have the curve y equal to fx. Well, this time I have the light blue one. This is the curve y equal to fx. and I have the tangent line here. Well, if I look at the point x and x plus delta x, so the difference is just delta x here that I label in yellow, but delta y is defined to be the difference of y from the curve, right? The difference of y from the light blue curve. So it's going to be the amount that I just labeled in green. And your dy is going to be the difference from your tangent line, right? It's going to be the difference of y from your tangent line. This is called dy. Well, again, you can see that when you look at the point that is near x, so that means when delta x close to 0, so the approximation gonna be better, and you can approximate your delta y by dy when when delta x close to 0. So the thing that we are going to carry on and use it later. So let's look at the definition of derivative here. We have f prime x equal to limit fx plus h minus fx over h, where h go to 0. Everyone know this thing because this is the definition of derivatives. So if I switch my notation from h to delta x, so I am going to have x plus delta x go to 0. So I just switch my notation from h to delta x, and now I can ignore the limit sign. I can say that f prime x is approximate by fx plus delta x minus fx over delta x, where delta x go to 0, right? It means when delta x is very small, so those two quantities, they are almost equal to each other, and then I can simplify this thing to f prime x times delta x is approximate by that, right? I can add fx on both sides, so I am going to get f prime x delta x add fx is approximate by fx plus delta x. Well, but delta x and dx are the same, right? So I can say this is f prime x times dx plus fx is approximate by fx plus dx, and bam, this is our equation that we are going to use for the whole section. So this is our formula that we are going to use for this section. So our formula is, if you want to compute the value of f at the point x plus dx, you can approximate it by using fx plus f prime x dx. This thing is called differential, right? This is dy, the one that we just defined on the previous slide. So this is called differential. All right, so here is the thing. If you understand what I just explained on the first 15 minutes, good, that is the proof. But if you do not understand what I just said in the first 15 minutes, all you need to memorize is in this box. Fx plus dx is approximate by fx plus f prime x dx. This is what you have to memorize, because this is what we are going to use to solve the problems. But to prove this formula, I just explained in the last 10 minutes. Well, so we are going to keep this formula and use it again and again and again until we are comfortable with this formula. All right, let's see how it works when you do real example. So let's look at the example 54. So I will use differentials to approximate 1 over 0 or square root 0.99 minus 0.99 to the 5th power. So let's suppose that you do not have calculator. You do not have a calculator. So you cannot check the answer. You just need to use the differential to approximate this thing. Well, this is what we are going to ask you on the homework and on the exam as well. So we want you to approximate something without using a calculator, because on the exam you cannot use the calculator. So we can use calculus to approximate this thing. I will show you how. So if you want to approximate this thing, you can see that the number 0.99, this is very close to 1. Right? So we are going to define our function. Let fx to be our function 1 over square root x minus x to the 5th power. Why do I need to define a function like this? Because if I define the function like this, then we need to find f of 0.99, right? This is what we want. So if I define the function like this, I want to find f 0.99. Well, that means let's look at f 0.99. F 0.99, this is equal to f of 1 plus negative 0.01, right? The reason why I do this is I want to split 0.99 into 2 pieces, which is x plus dx. Because I hope that if I split it to fx plus dx, I am going to use my approximation to be fx plus f prime x dx. That is what I want. So here I have my x is equal to 1. And I have my dx equal to negative 0.01. So that means I am going to approximate this thing by f of 1 and then plus f prime of 1 times dx, which is negative 0.01. All I need now is I need to compute f1 and f prime 1, right? So I'm gonna make a note here. So I have fx equal to 1 over square root x minus x to the 5th power. I have fx equal to x to the negative 1/2 minus x to the 5th power. So if I differentiate one time, so I get negative 1/2 x to the negative 3 over 2, right? And then minus 5x to the 4th power. Well, that means if I compute f prime 1, so I am going to have negative 1/2 times 1 minus 5 times 1. That is my f prime 1 is going to be negative 11 over 2. So I have that. And also I can plug in f1. So I can compute my f1 here. So I plug in number 1 into the equation. So 1 here, I get 0. Right? So I also know that f1 is equal to 0. So I am going to use f1 equal to 0 and f prime 1 equal to negative 11 over 2. And then I plug in back to this. So I am going to get 0 plus negative 11 over 2 times negative 0.01. Well, and negative 11 over 2 is 5.5. And then if I multiply negative 5.5 and negative 0.01, so I get negative, or not negative, positive 0.055. Well, this is my answer. Well, that means after I use differential, so I can approximate 1 over square root 0.99 minus 0.99 to the 5th power by using differential. I approximate this equal to 0.055. And if you have calculator with you now, so you can try to check your answer. Well, if you plug in this thing into calculator, you're gonna get the number that is close to my answer here. This is what we use calculus to help us to approximate. Does it make sense? Let's suppose another thing. Let's suppose that I want 1 over square root 1.02 minus 1.02 to the 5th power. Here, that means I want f of 1.02, right? Because if I plug in 1.02, I'm done. So that means I can separate 1.02 to f1 plus 0.002. And for this question, my x gonna be 1. My dx gonna be 0.02. And by using the approximation, I can approximate this thing by f1 plus f prime 1 times 0.02. Make sense? And then f1 is equal to 0. F prime 1 is equal to negative 11 over 2. And then 0.02. And then I compute this thing, so 2 cancel, so I get negative 0.11. So that means if I want to approximate 1 over square root 1.02 minus 1.02 to the 5th power, I can approximate it by using differential, and my answer is going to be negative 0.011. Sounds good? Well, the idea is you need to construct your function first, and then after that you trying to apply the approximation formula. That is the key point. Well, if you still do not understand, let me show you another example here. Let's say that I have, let's say fx equal to square root 5 minus square root x. And let's say that I ask you to compute square root. Let's say I want you to compute I want you to compute square root 5 minus square root 0.84. For example, like that. How do you compute it without using calculator? Without using calculator. Well, the question or the exam gonna ask you to use differential to compute this thing. So that means, hey, I want to compute this thing, right? So I can define my function f to be this function. And once I define my function f to be this function, so that means what I want to compute is f of 0.84. Make sense? I want to compute this thing because it is f of 0.84. And then you compare with the differential form. This is 1 plus negative 0.16, right? Because it number 0.84, this is close to 1, right? It's just 0.16 short from 1. So you just add that thing. And then after that, by using the formula, so you can view this thing as fx plus dx, right? By formula, this is going to be fx plus f prime x dx. Well, that means I have the approximation to be f1 plus f prime 1 times negative 0.16, right? And then you delete that line. Well, and then you can compute f prime 1 and f1. You can compute it by using calculus technique. So you're gonna get this two number, and then after you got those two number, you calculate this thing. That is going to be your final answer. For sure, you're gonna see the question like this again and again when you review our exams or review our the problem before the exam. So make sure you can do this thing, but the key point is the approximation equation is this fx plus f prime x dx. When you split 0.84 to 0.16, you have to be smart to split this thing. So we're gonna split this thing into the number that is easy to calculate. So some student gonna ask me, Ajahn, can I split 0.84 to 2 plus negative 0.1, 0.16? You can, but for this case, this is not going to be a good choice. Not a good choice, because if you do that, so when you compute f of 2, so you're gonna end up with square root 5 of square root 2, which you still don't have a calculator and you cannot compute this thing easily, right? Compared to if you use 1, so you're gonna get square root 5 minus square root 1, which is a lot easier because you can compute that thing by hand. It's gonna be square root 5 minus 1, which is square root 4, which is 2, right? So to choose the point, you try to choose the one that close to the point that you want to approximate, and that number is easy to compute. So that is all I want to say about differentials formula. Well, hope you can do this thing. So the practice for this thing gonna be in homework 3. So homework 3, we're gonna start by looking at differential here. All right, so let's do more examples. We're gonna look at the application and some complicated problems on using differentials. All right, so let's look at example 55. So this is the one that I just copied from the book. I will show you how it's works. So let's read the question first. So I have that the radius of a sphere was measured and found to be 21 centimeters with the possible error in measurement of at most 0.05. The question is, what is the maximum error in using this value of the radius to compute the volume of the sphere? So you know that, well, you have a sphere. You have a sphere, which is this shape, right? And when you have a sphere, your equation gonna be V equal to 4/3 pi r cubed. This is going to be our equation that shows the relationship between the volume and the radius, right? We have our radius r and the volume gonna be V. So from that, you can find the differential. So we're gonna find the differential of V with respect to R. So that means I do not need to differentiate 4/3 pi because this is constant. So I just need to differentiate R cubed. So I get 3R squared dr. Because I differentiate R cubed and then 3 cancel. So I have 4 pi r squared dr. So this is the differential of V, right? Which is given here. And then you can look now that the question said that the radius is 21. And we also know that actually the radius is 21. And we actually know that the possible error in measurement is at most 0.05 centimeters. So when you measure your R, so you can have the error and the maximum error is going to be 0.05, which means absolute dr is less than or equal to 0.05, right? So dr is the change in radius. This is the change in radius, right? We say that it is not going to be bigger than 0.05. So if you want to compute absolute dV, this is the change in volume. So the change in volume is not going to be, well, let's say the change of volume is going to be absolute 4 pi r squared dr, right? And this is going to be 4 times pi times 21 square, and then absolute dr. This is not going to be bigger than 4 times pi times 21 square times 0.05, which is equal to 277. So that means your volume, the maximum error of the volume gonna be about 277 centimeters. Does it make sense? This is one approximation that you can do. One application that you can do. So you can see that here we just use a differential to calculate the maximum error in volume if you know the maximum error in radius. So let me give you another idea here. So from the last question, we know that given differential of r is less than or equal to 0.05 and I equal to 21. So we show that our change in volume dV is not going to be bigger than 277 approximately. Well, sometimes this number is hard to interpret because sometimes you just don't know how much it is compared to the original. So sometimes we are going to define the thing that we call relative error. So relative error, actually this is going to be delta V over V. And that is approximated by dV over V, right? And dV over V here, well, if you are trying to compute for this question, dV is going to be 4 pi r squared dr. We just compute it on the previous slide. And V, this is going to be 4 over 3 pi r cubed. So you can cancel this thing. After you cancel, you're gonna cancel pi, cancel r squared r cubed. So you have r on the top, on the bottom, sorry. So you're gonna have dr over r here, and 4 cancel 4. So you have 3 times dr over r. Well, that means absolute dV over V is not going to be bigger than 3 times 0.05 and over 21. Because I just plug in the value of dr and r equal to 21 here. Well, I compute this number, that means 0.007. Well, that means the relative error, the maximum relative error, this is going to be 0.007. Well, if you don't like relative error gonna give us the sense of how the volume change compared to the original volume. But if you don't like it, you can switch to percentage error. So if you want percentage error, this is going to be delta V over V times 100. Well, just multiply 100 to get the percentage, right? Or it's approximate by dV over V times 100. Well, for this question, so it is the absolute dV over V times 100. This is not going to be bigger than 0.7%. Because I just keep this number and then I just multiply 100. So I have 0.7%. So the maximum percentage error, this is equal to 0.7%. So it's just another term that we use to describe the error. So they can ask you to find the error, which is just dV or something, or they can ask you to find the relative error or percentage error. So let's do one more example, and that will be end for this chapter, and then we are going to wrap up what we just learned. All right, so let's do another example here. Well, this is, 1 second, it's going a little bit slow. So this is example 56. So the question said that I have a cube and the edge of a cube was found to be 30 centimeters with a possible error in measurement 0.1 centimeter. We want to use differential to estimate the maximum possible error, maximum relative error, and maximum percentage error in computing the surface area of the cube. So first of all, you look at the cube you have. This is your cube. And for your cube here, you know that the edge is measured 30 centimeters, right? However, you have the, let's say that let x be the length of the edge. So you know that x is equal to 30 centimeters, right? However, you also know that 30 centimeters here, you can have a possible error of measurement of 0.1 centimeter. So that means your absolute dx is less than or equal to 0.1, right? It is possible that your number 30 is not exact. It could have an error, and the error is not going to be bigger than 0.1 centimeter by the problem. So what we want is, we are looking for the surface area of the cube. So how do you compute the surface area of the cube? So the surface area is going to be, for sure, I need that, right? That cube. So I need to compute the surface. Well, how can you write the surface area in terms of x? So type in the chat now. What is your guess about the function of the surface area here in terms of x? All right, someone says 6x squared. Is everyone? Oh, no, okay. 6x squared, 6x squared, 6x squared. So if x is your length of the edge, so your surface area, I am going to define this thing to be my A, because it is area, right? So I'm going to say my A. That is going to be, well, seem like everyone says 6x squared so far. So yes, it's going to be 6x squared, because on each side here, so you're going to get x squared, right? And then you have 6 sides in total. So that means the surface area is going to be 6 times x squared. So you have the relationship A equal to 6x squared. That means you have dA, which is differential of A. This is going to be 36x times dx. No, not 36, sorry. 6 times 2 is 12. Sorry, 6 times 2x, that is 12 dx. So this is 12x dx. All right. And then after that, so you want to compute your absolute dA, right? Which is going to be absolute 12x dx. And you know that 12 is constant, your x is 30, and then your absolute dx here. And then you know that your dx is not going to be bigger than 0.1. So that is 12 times 30 times 0.1. That number is 360 times 0.1. This is 36. So that means your maximum possible error. Maximum possible error. This is equal to 36, right? Because you already compute the A here. So let's look at your maximum relative error. What is your maximum relative error? So that means you have to compute absolute dA over A, right? Because you're gonna compare how the surface area change compared to the given surface area. So the dA is not going to be bigger than 36. We just compute on the previous question. And then your A, surface area, is going to be 6 times x squared. X is 30. Right? And then once you use your algebra skill to compute this thing, this is going to be 6 over 32 times. And that means 6 over 1 over 150, right? And that is equal to 0.0067. Well, that means the maximum relative error is 0.0067. And then also the maximum percentage error, this is going to be 0.67%. Well, on the exam, we may ask you possible error, relative error, or percentage error. So, well, the idea, you just need to find the possible error first, and then if you want to compute the relative, you just compare it relatively to your original function. All right, and that is another example for using the differentials for some approximations. All right, so I think we are going to end the content here for today. So for the remaining time, we are going to do a review what we did on the first few weeks and what are we standing at now. So before we do that, 43 students here, do you have any questions? No, type in the chat if you have any question. If not, type in the chat you have check-in today. So type check-in today in the chat now so we know that you are in today. And I told you that for the remaining time, I will hold you for 20 more minutes. So let's look at what we did in the first few weeks. And this is where we're standing at now. All right, are you ready? So this is what we have done so far. So on the first 2 weeks, we talk about limits. So this is my expectation. So for now, you should be able to find the limits from the graph. You should be able to compute one-sided limit. You should be able to apply limit laws, including factoring, conjugation, and using the can do the problem related to absolute value limit. Also, I expect you to compute the infinite limit. Well, I mean, you know how to show your work when your answer is going to be infinity or negative infinity. And also you know how to compute limit to infinity. And also how to check the continuous at the point and on the interval. So for the whole part here about limit, it's going to be 20% of your midterm. Next, on week number 3, we just learned definition of derivatives. This thing you learn that we can use limit of fx plus h minus fx over h, where h go to 0, or we can use limit x go to a, fx minus fa over x minus a. They are equivalent. So if this is my notation for the derivative, right? The definition of derivative. This is at the point A. So they are equivalent. Well, you should be able to find derivative by using definition. And on the case that you usually use the definition is the one that you have to work with left hand and right hand derivative. Remember that we just learned f prime a minus and f prime a plus. This is left hand and right hand derivative. So if they are equal to each other, of course, the derivative exists. And also we learned the geometric interpretation of derivative. By this I mean we learned that the derivative is a slope of the tangent line. So if we ask you to find the tangent line, the equation of the tangent line, you should be able to give it back for me because you know how to find slope, and you just put the slope and the point that the line passed, and then you just build up the equation and give back to me. And also the big part that we learned is the chain rule, which you should be able to apply the chain rule, which is f prime, f or g prime here of x. This is going to be f prime gx times g prime x. This is what we just learned, I think last week for the chain rule. Well, this is very important and you are going to use it again and again. So, and the last one we learned here in this part is higher order derivative. You should be able to compute derivative so many times and then guess the general form of the n order derivative. So for the whole part here, this is going to be another 20% of your midterm. Well, 40% now. Another 20% of your midterm. This is the third part of your midterm. This is going to be implicit differentiation. This is what we just learned on Monday. And also it's going to be derivative of trigonometric and inverse trigonometric functions. Trigonometric here, this is sine, cos, tan, cotan, cosec, and secant. No formula is given. So you need to memorize everything. But as I told you that memorizing the formula is not that hard because it's somewhat easy to memorize because you know the pattern is there are patterns in the formula of trigonometric and inverse trigonometric function and also inverse trigonometric function as well. So it will take a while for you to memorize and be comfortable with trig and inverse trig, but here we go. I mean, you will get better by the time. And then the last topic on part number 3 is going to be differentials and linear approximation. So keep in mind that your friend is the equation fx plus dx. This is approximate by fx plus f prime x dx. And the last piece here, this is called differentials. All right, that is all 60% of your midterm now. So 60% of your midterm now that you already learned. So you need 40% more. When we come back next week, we're gonna start learning integration, which is 40% more. And also chapter 4, which is more complicated stuff about differentiation and integration. So, but for now, we have a long break this week. So you should be able to review and, you know, do the practice problems to make sure that you are comfortable with this 60% of your midterm. So I have 6 problems here. This is our O exams, adapt from the O exams. So let's take a look very quick. So this is adapt from the O exams. So let's see if you think that this is way too easy or too hard for you. So question 1. So I have y equal to f of x to the 5th power minus 2x and f prime t equal to 1 over 1 minus 2t. And I want you to calculate dy by dx given that x equal to 1. So you can try it at home. by using the chain rule. So this question we ask you to apply the chain rule, right? And the answer is 1. So you can see that y is a function of this thing, right? So you can define this thing to be your u. And once you have y is a function of u and u is a function of x, so you can find dy by dx by the chain rule. So try it. This is considered as a medium one on the exam, not hard. So well, if you cannot do question 1 here, you can ask me later. But this is the same difficulty level that you're gonna see when we give you a test. So question 2, given the curve, this curve, if y is a function of x, can you find the equation of the tangent line of the fx at the point here? So for sure, when you see this function, this is the implicit form. So you do not need to simplify the implicit form to the explicit form. This is going to be way too hard. So my suggestion is that you should do the implicit differentiation, and then you plug in x equal to -1, y equal to 2, and solve for y prime. So you're going to get your slope, and once you get your slope, you can build the equation, and the answer is here. Easy, right? So another question, this is medium to hard one. So let's say that you have fx equal to that. The question says if you know that f2 exists, f prime 2 exists, it means you have derivative at x equal to 2. So can you find the value of a and b? So how could you find it? So you have two variables, I mean two constants, a and b. Well, because you know that the derivative at 2 exists, well, if you know that the function is differentiable, that means the function must be continuous at x equal to 2 as well. This is the key point, because most students gonna know that, yes, the function is differentiable at x equal to 2. So that means f prime 2 minus is equal to f prime 2 plus. When you set up this equation, you're gonna get only one equation. But you have two unknowns, right? One equation is not enough. You need another equation, and it's gonna come from continuous property, because you know that derivative implies, differentiable imply continuity. So that means the function is also continuous. So you can also use limit of fx, where x go to 2 from the left, equal to limit of fx, where x go to 2 from the right. So this question is medium to hard. Well, usually B plus student and A student can do it. But, well, let's see if you can do that one. So this is the answer. So try it at home. So question 4, we are going to look at the differential here. I want you to use differential to approximate this thing. Yeah, for sure. Why not? Why don't we define fx to be x to the 1/3 plus x to the 1/2, right? And you want to find f63.52. As I told you today, you need to find a point that is close to 63.52. That is easy to compute. Well, I say 64, right? Because, well, the reason why I choose 64, because if I choose 64 here, it's gonna be easy to compute square root and also the cube root, right? This is a good way to do. And when you approximate, so you should get the answer 11.16. Well, you can try doing f63 60 plus 0.52, but this is not a good choice, because once you do that, you're gonna end up with 63 raised to the 1/2, and you cannot compute it by hand. All right, another two questions, the last two one. So let's say, suppose you have this equation, right? And then this is not that hard, so we are going to ask you to find the equation of the tangent line. Again, you can try this question. This is our exam as well. So your answer is going to be this one. And the last one, practice of the chain rule together with differentiate trigonometric function. So you're going to get this answer.